My name is Kregg Egan. I'm a manufacturing applications engineer. I'm going to discuss important topics to help successfully machine your own parts. But first, what are some advantages and benefits of machining your own parts? The most obvious advantage is having full control of the process. This means that you can decide to revise a part at any time to make it easier or faster to machine, or to use a less expensive material or one that's easier to machine. These are all contributing factors in the overall cost, time, and efficiency in producing a finished part. The benefits you will gain might not be as obvious, but they consist of gaining a better understanding of some of the challenges involved, like how important proper work holding is, how to reduce setup times and the amount of setups, and how to get the best surface finish. You will also be able to accurately estimate the total cost and time it will take to machine a part, which ultimately saves you money. Knowing how to machine your own parts is very rewarding and beneficial, but it's important to understand what it takes to successfully machine a part. My hope is that what you learned today will give you a better understanding of what to expect as you first get started, and to put things into perspective, to give you the confidence to start machining your own parts. First, I want to show you how to program a part, then discuss some topics that influence how we program and machine our parts. Solidworks Cam is an add-in directly to SolidWorks. If you go to your add-ins, you'll want to make sure that you have SolidWorks Cam selected. Once you do, you'll have 3 extra tabs that are all related just to SolidWorks Cam, and you will have a SolidWorks Cam Command Manager tab as well. The first thing we're going to do is edit the machine definition. We're going to right-click on Machine and select Edit Definition. We're going to verify that we have the correct machine selected. We can choose from different tool cribs that we might have. We want to verify that we have the correct post-processor selected. The next thing we'll do is define our stock definition. And new in 2021, we have 2 more options for defining our stock definition. The first option allows you to select from a list of predefined custom sizes, which can also be saved according to the stock material selected. Depending on which one you have selected will determine what options you have to select from in the drop-down. We can create our own custom profiles. For this part, I will show you what that looks like. So we have now a Save to TechDB option. I can select this. I can give it a name. I could say, I'm going to say my custom name. We could place a description. So if you have a reference to the stock material itself that you use, you could put it here. You could also put it under the stock ID. And here on our stock material, this is where you could list it to be material dependent. I'm going to leave it set to all and select OK. Now moving forward in this drop down, I now have the My Custom Name. I know that's not original, but I couldn't think of anything better. So that's how we can create our own custom profiles, and this can be changed and edited at any time. You can again select the Save to TechDB and rename it, choose a stock material, whatever you prefer. The second option I want to show you on a different part. All of this can be done using a mill, and I want to put it in this Call It holder, which is going to require a round piece of stock. So I'm going to edit the stock manager and show you the second new feature added, which is cylindrical. I can determine which direction I want that to be in. I'm going to place it in the same way as my coordinate system. And again, I can make this whatever size I want. I can use these offsets down here as well. Give me a little bit of stock on top and on bottom. And now I quickly have a round piece of bar stock. This just saves us that extra bit of time, which all adds up. So let's go back to the other part. I'm going to change the stock to bounding box and give a little bit of material in the positive Z direction. I've already created a Solidworks coordinate system, and that's what I'm going to select from. In Solidworks Cam, we have automatic feature recognition, which will find 2.5 axis features of your part. In this case, it will recognize a face feature, the holes, the pocket, and a perimeter feature. We can change the options to have it only find specific features. So I want to verify what my options are set to have better control over what it looks for. I'm going to go into my options, and I can see that holes is not selected, so that means that these holes would not have been found. I'm going to activate holes, and the rest is how I want it. Now I'm going to go to my Command Manager tab and select Extract Machinable Features. This is the automatic feature recognition. Here it's found the face feature, the rectangular pocket, and the hole group. They're all the same size holes, so they were grouped together. Now we have features. Now we need to generate the operations for the features. In these brackets, these are referred to as strategies. The strategies are what make up the operations, and the data that we get from the operations is pulled directly from the technology database. Once I select Generate Operation Plan, it's pulling this information from the technology database and populating it here for me. So now we have operations. These are what control the toolpath and the settings for our toolpaths. I'm going to leave everything default, and I'm going to select Generate Toolpath. And now I can hover over each one and we can see what the toolpath is doing. Also new in 2021 for our center drills and drills, inside the operation, we now are able to specify the peck amount by either entering in a value, percentage of the tool diameter, or percentage of the flute length. This helps give us better results depending on how deep a hole is, how big the hole is, etc. More flexibility in the long run, which is great. I'm going to go ahead and simulate the toolpath. This is my stock profile. I'm going to press run, and we're going to see the tools cutting the part. Now that it's done, we have a comparison tool. This is going to show us the difference between the part file compared to the stock profile. That's going to check for gouges or leftover material that still needs to be machined. Anything here that's green, that's cut perfectly to size. Anything in this turquoise to blue range, that's going to be leftover material. And the yellow to reds, that's going to be a gouge. Here we can see we're right on the money. Once we're satisfied with our toolpaths, we can edit our mill part setup, and we can select where to put our work offset. That's where our 0, 0 is going to be once it's in the machine. Here I've got it set to fixture coordinate system, but I have many different options on where to place it. We can select stock vertex, and it'll remain on the top left corner of the stock. We can change which corner that is using these radio buttons. Then in our axis tab, if we wanted to rotate the X and Y axis, we could do so by using any of these options, but I want it left as is. In our offset tab, here's where I can specify a work coordinate. So if I want something other than G54, I can set it here. If it's left to none, it will default to G54 automatically. Since I moved the work offset, it needs to recalculate all of the toolpaths. I'm going to select yes. Now, when it's in the machine, that's where our 0, position will be. Now that we've defined our work offset, and if we're satisfied with our toolpaths, we're ready to post-process. I'm going to go up to my Command Manager tab, select Post-Process. We need to save the file. I'm going to go ahead and run, and I'm going to select OK. Now I can see and review my G-code and make any changes necessary. And this is what we take to the machine to run our program. One more thing I want to show you, which hits close to home for me, is new in 2021. They've added a feature that's, in my opinion, a good safety feature. What I mean by that is we've already set where our work offset's going to be, and everything is going to be calculated from that position. So if I come in here, and I'm going to make a drastic change so that it's obvious, and I increase my stock, I'm going to select OK. Now, this pop-up warning message is new to 2021. This is showing that the stock parameters have changed, and it's saying, do you want to rebuild the Solidworks Cam items which were affected by the change? It actually shows me what was affected. If I say yes, it will update automatically, which is great. If I say no, it's going to at least give me these exclamation marks showing me that it's not up to date. The reason that this hits close to home for me is that this is how I first crashed a machine. The very first time I crashed was I did just this thing. As you can see, our work offset's down here still, but our stock has now changed to be much higher. Now, depending on the situation or the scenario, this is going to cause a big problem. And that's why I'm so glad to see that they now have a warning message as well as these exclamation points to tell you that something's not in sync. So let's try that again and let's allow it to rebuild. I'm going to change the stock just a little just to get that pop up again. This time I'll select yes. Now we can see my work offset has changed correctly to my stock profile, and there are no longer any exclamation marks. So now you don't have to make the same mistake I did. Now that you've seen a quick demonstration on programming a part, I'd like to discuss the topics that influence how we program and machine our parts. First, you need to develop a game plan, a strategy from start to finish on how you will machine the part. Here's a list of things to take into consideration. The size and shape of the stock determine the possible work holding methods. So you should be thinking about what the stock will look like after the setup has been machined according to the work holding method used. As an example, if we took this part, put it in a vise, and machined the first setup, what would the resulting stock profile look like? With this mental image, I can determine that it will require different work holding method for the second setup to remove the excess stock because the part does not have two parallel sides for the vise to hold once we try to machine the second setup. At this point, you must make a decision to either figure out what you'll do for the second setup or rethink your strategy for the first setup so that it's more accommodating for the following setups. What will my work holding method be? Some of the things to consider when choosing a work holding method are how rigid will it be, how long will it take to set up, and can it be used for more than just one setup? Based on what we saw, placing that part in a vise for the first setup will require an additional work holding method, which sometimes there's no getting around that, but I have a better solution for work holding that will only require one method for both setups. It involves using a fixture plate, which the part will be fastened to. The first step is to drill the holes in the fixture plate, making sure they accurately align with the stock. Then drill and tap the holes in the stock. Then I can pass the screws through the fixture plate and screw them into the tapped holes of the part to fasten it securely to the fixture plate. This method allows me to machine all the features in the first setup, as well as the second setup to complete the part. I want to show you what the process looks like using Solidworks Cam. To keep things organized, I've created a configuration for each step required. The first step will be facing the top of the stock, drilling and tapping the holes. I'll go ahead and simulate this to give you an idea of what this will look like. That's all we're going to need out of this setup. So let's switch over to the fixture plate. I've used the hole wizard to properly align the holes to the part. I just needed a center drill and a drill operation for this. I'll go ahead and simulate this. So we just have 3 holes for this one. Now let's look at the entire thing together. And because everything's been cut to size, except for just a couple features, all we need is a perimeter feature, a roughing feature for the inside pocket, and a contour mill for the counterbore. Let's go ahead and simulate the toolpath. And that gives us a completed first setup, which then we can reverse the fixture plate and machine the second setup to completion as well. This goes to show that different work holding methods can make a big difference on how efficiently we can machine a part from start to finish. Let's discuss a topic that can influence what work holding method we can use. Before you can make a final decision on a work holding method, you have to take your tooling into account. Let me show you an example of how tooling can dictate the outcome of a game plan. This part has 2 slots, which could be machined with a keyway tool, requiring only 1 setup. But if you don't have a keyway tool, it will require 2 setups using a flat end mill. Another common scenario, which can force you to be creative, is when you don't have a long enough tool to reach all of the features from 1 setup. So keep in mind any tooling limitations you may have while creating your game plan. What about the material? You must factor in the type of material being used, and here's why. Steel materials will require a more rigid work holding method, whereas plastic materials don't require as rigid of work holding, but are prone to flexing and susceptible to heat, which can make it difficult to keep tight tolerances. The type of material can also dictate how many setups are required and what type of work holding is used, which is why it's important to be mindful of this during the planning stages. All of the topics I discussed need to be taken into account equally, as they're dependent on each other. This brings us to another topic. Be prepared to adapt. Set an expectation that there's a good possibility you will find yourself going back to the drawing board on more than one occasion. Don't commit yourself to just one idea. You need to be willing to rethink your strategy at any time. All it takes is one broken tool with no spares left, and it'll force you to come up with a plan B. And yes, that actually happened to me. It's always helpful to get a second opinion. Ask someone to give you ideas on how they would do it. So what's next now that you have a game plan? There's a saying in the CNC community which says there's 2 types of machinists: those who have crashed a machine and those who will crash a machine. In case you're unfamiliar with that saying, it means you'll crash a machine eventually, but there are ways to minimize the frequency and severity of a crash. First, read the manual for your machine. Next, read the manual for your machine. Yes, I did say it twice because it's very important that you know how your machine works. Be familiar with basic G-code commands. Review and verify the NC program to be sure it's accurate and to know what to expect from your machine as it runs the program. Make a checklist of tasks that need to be done prior to running a program and cross them off as you go. Tasks such as whether the correct tool is loaded in the correct station number, or setting your work and tool length offsets. Start small. It is not recommended that for your first project, you attempt to port the intake and exhaust manifolds of your wife's car. Machining a plastic 2-inch block with a hole in the center is a good starting point. Always start slow. It's standard practice to decrease the rapid speed when running a program for the first time and to have your finger in position ready to press the stop button at a moment's notice. Now, it's time for some real talk. Many people getting started for the first time have told me that they highly underestimated what it takes to successfully machine a part. Machining is more of an art than it is a science. This doesn't mean you have to be an apprentice at a machine shop for 3 years to be successful. It means that you should have an expectation that you're going to have some trial and error ahead of you, as well as broken tools and scrapped pieces. This can easily become frustrating, discouraging, and take a toll on your confidence, but do not give up. This is a mandatory process to become successful and efficient at machining, which no one is exempt from. My advice is to take Thomas Edison's advice. He says, "I have not failed, I've just found 10,000 ways that won't work." Many of life's failures are people who did not realize how close they were to success when they gave up. There's a way to do it better, find it. Let's switch gears and talk about G-code. It's the type of code used to tell a machine what type of action to perform. Think of it as a set of instructions for a machine to follow. In order to produce G-code, a post-processor must be used. A post-processor's role is to translate the toolpaths we created into a language that the machine can understand, which is referred to as an NC program. This is where the G-code resides. The NC program can be loaded into the machine's controller to run the program. The machine's controller plays an integral role in the machining process since its main function is to execute the NC program by controlling the machine's motors and auxiliary functions such as coolant and tool changes. There are several different manufacturers who make controllers, and they each have their own unique way of reading and executing G-code. This also means that post-processors are not compatible between two different types of controllers. Here's a side-by-side comparison of an NC program for different types of controllers. These NC programs were all created using the exact same toolpath, but using a post-processor designed specifically for each controller. At first glance, they look drastically different from one another, but on closer inspection, you'll notice they're actually very similar, using mostly the same G and M codes, with the major difference being their formatting. The way an NC program is formatted is critical to a successful outcome, as there's no such thing as close enough when it comes to formatting. It has to be precise, using the correct G and M codes in the correct order. Otherwise, you will be vulnerable to unexpected outcomes, also known as a crash. For this reason, I've put together a list of common G and M codes that will be in almost every NC program you run. I highly encourage you to memorize these, as well as keeping a complete list of G and M codes nearby to reference it when needed. I want to thank you for watching. and I hope you found it helpful.